Ladies and gentlemen, it's time to kick off the next session here. So we go from event to access in events. Please give a warm hand to Marc Klefter.
All right, welcome everybody to this talk. I should say if you attended the previous talk, you'll probably find this to be a nice follow-up. It touches on this sort of the same topics. So my name is Marc Klefter. I'm the CTO of a consultancy firm called Edgement, where I spend quite a lot of time helping our clients implementing message-driven systems. And probably some of you have experienced this in your own work. How many of you have done any type of pub/sub with events in your line of work? Quite a lot of hands. However, I would hazard a guess that access control, or performing access control when you consume and process an event, might not have been top of mind. Or it might have. Any hands? A lot fewer, as expected, because I find this to be generally the case that this topic of access control in event, or more generally message-driven systems, is something that is largely ignored. A lot of people also ask, why is this even something we need to care about? In this talk, I want to not only explore this topic, but also hopefully provide a very good motivation for why we should care, and more importantly, how we go about addressing it. So let's just see what we're going to cover in this talk. So we're going to talk about access control in the context of zero trust. And zero trust is an emerging security model that has gained a lot of traction in the last couple of years. And basically, it's a way to reason about users and applications, devices, those kinds of entities, using a more hard-lined approach, I would say, in terms of, as the name implies, do we trust these entities, specifically what they're allowed to do inside of our network environments. And since we're talking about messaging, it's useful to know what types of messages there are. So we're going to take a look at 3 types of messages: commands, events, and queries, and the semantics of each. In order to perform access control, we need some plumbing infrastructure for writing policies, for testing them, packaging, deploying, and ultimately enforcing them. We don't have to implement this ourselves. We can use a technology such as Open Policy Agent to help us out. And with that, we can go about actually implementing zero trust for asynchronous communication, which is what underpins message-driven systems. So it's always helpful to have a proper frame of mind when tackling any subject, such as this one. So we're talking about access control, or more commonly named perhaps authorization. And this entails using some kind of identity, often for some user, that we can verify. And this identity carries not only who the user is, but claims associated with the user. And we can use those claims, attributes, to see whether this user can perform some type of action on a resource. And the types of attributes that can go into a decision for allowing or denying an operation on a resource is not only the ones that are tightly associated with the user. It could be something, of course, having to do with the resource itself and the surrounding environment in which the operation takes place. So all of these go into evaluating a particular permission policy. The type of system that we're looking at is one that is composed of services. I'm specifically avoiding the use of microservices here, but generally components we can term as services that interact in a distributed fashion. Often you will see in these types of systems that services are logically grouped to support a particular part of a business domain. So some services are grouped together, for example, when you implement the inventory subdomain for a retailer, perhaps, much like you have a shipping subdomain and services to collaborate to enable that type of business function. So you have communication not only inside of those subdomains, I call them trust domains. So there's some sort of trust implicitly inside of those separate subdomains. And then you have the problem or the concern of also enforcing trust across subdomains, across these groups of services. This also means that inside of a trust domain, we can have a permission model that completely differs from the one we use in another one. In one subdomain, we can have a role-based access control model. In another one, we can have a more loosely defined model that works with attributes in general. We'll see more of that later. And finally, the type of communication style we're looking at is asynchronous, of course. This means that when we have services that interact with each other, they do not do it directly. They're always decoupled through some sort of broker for commands, events, and queries. Given this setting of the stage, let's look at how we deal with zero trust in the synchronous scenario. But first, we must also know what we mean by zero trust more specifically. There is an old saying, trust but verify. Zero trust is the more stringent approach where we never trust anything but always verify everything. Sounds good in theory, hard to accomplish everywhere in practice. But what it means is that the data that is communicated inside of a network environment is not to be trusted, especially when it comes to basing operations on that data. So just because something gives rise to an event that we need to process and subsequently execute an operation, this should not be allowed or thought of to be allowed from the outset. Why has zero trust emerged in the recent years? It's coupled to the fact that the types of systems we're building aren't exactly trivial anymore. Distributed applications are complex. They are dynamic in terms of how they are composed, how they evolve. They're independently developed and deployed when you talk about services. They can run in the cloud, on-prem, or using a hybrid model. You're using a container-based approach or serverless. You have multiple entry points. It's quite far removed from maybe the type of systems we used to build in the past, monolithic single-process applications. Moreover, we have a separation of security layers, one dealing with network security and one with application security. What is network security? VPNs, firewalls, security groups, network access control lists, identity and access management is part of that as well. That is something that we have very knowledgeable network security engineers for, but we as application developers are not really concerned with that. We just hope that that is configured appropriately for the network environment in which our applications run. We, however, are more concerned with the user identity, or identity also maybe of another system, that we can verify and where we can use certain claims to authorize an action, say. These two layers, especially representatives of each, seldom communicate, or at least not effectively. And this gap is also a large source of the problems that we face. And it's simply the case that once something reaches inside of our network environment, simple request, you have to consider it a threat according to zero trust. Imagine just a simple analogy like your home Wi-Fi network. You've probably secured it, but you get a friend over who wants to log on to the network. Being the good friend you are, you share your password. You have no idea what goes on with that person's laptop in terms of malicious apps or products that person uses. So suddenly you have a threat model that you need to be aware of. It's very common that that happens inside our corporate environments as well. So given that we need to tackle the issue of zero trust, again, let's take a look at the synchronous case. I'm not going to go into too much detail about what an access token is, in this case a JSON web token. Let us just say that this is something that is produced given that a user has been authenticated. This token can now be used for authorization, so you pass it as part of a request to an API gateway. This token is then validated in an authorization service. Being the proper good stewards of our network environment, we exchange that incoming token for another token that is only valid inside of this trust domain, inside shipping, say. So this second token in pink is then forwarded to our first destination, which is the API service that supports the REST API, say, that we expose. This API service, in turn, calls a downstream service, simply called service in this slide. Now, you see that we have already one layer of defense here, mutual TLS. So the API service and the downstream service, they can mutually authenticate, meaning they're allowed to simply communicate at all. But this doesn't cover the application security part, which is why we also pass along a token in this request, which is validated in the downstream service. This is very common, and it's characterized by the invocation being short-lived. So this invocation might succeed or fail. Either way, you're done in a reasonable time frame, so to say. This is important. We also typically don't implement long call chains because that has cascading effects that we want to avoid. So this effectively implements zero trust. But the asynchronous case is slightly more difficult. We have the same setup with tokens and token exchange. But now the API service, instead of a direct REST call, say, publishes an event onto a broker. That, in this case, is consumed by the downstream service. We're still using MTLS and maybe some access control list functionality on the network layer. But this is typically where you lose the identity context. You see that the pink token is not propagated. That's what I typically see in these types of systems. There's an important property here called location transparency. It simply means that when you publish some type of message, an event, say, you do not know the destination, the name of the destination, how many destinations there are for this event. It could be one downstream service or many. From an architectural standpoint, in terms of evolvability and so on, it's a very nice property to have. But in this case, it poses some problems because we do not know who will consume the event, for what purpose, and when. And the when part is especially important to acknowledge because, as in the previous talk, we saw that we could have complex workflows that last for hours, days sometimes, involving many different steps along the way. Might also require manual intervention to approve something or not. Workflows can be paused, resumed, retried in terms of failure, etc. All of this poses some problems for us when it comes to authorizing certain actions somewhere further on in the workflow. So we'll see how we address this in a bit. But I mentioned event as one type of message, but commands and queries are the other ones that we need to be aware of. So let's start with events. They're the simplest one because they're one-to-many. Follow a pub/sub model, and you expect no result when you publish an event. Commands are for, again, processing, validating some action that is to be taken. Commands are point-to-point in a way. You're supposed to consume it in one handler only, not many. And you get a confirmation, typically an acknowledgement that this command has been processed successfully or not. You can think of it the async request reply. The way it's implemented usually is you have two message channels, one for the command request and one for the command reply. You generate some correlation IDs that you tack on the command request. When it's processed and you get a response back through the second channel, the correlation ID is again included, so you can match it on the client side and process the response properly. This is usually abstracted into something you can call a command bus, so you don't really need to care about those details if you use the proper framework or plumbing. Much like commands, you have queries. The semantics are quite similar. Maybe the one that is especially fun to look at are subscription queries, where you can issue a query and then get results over time. But by and large, I'm going to treat them the same and focus solely on commands and events. So let's imagine a workflow that is completely message-based. Assume now from the scenario we saw earlier that we have an API service that wants to call a downstream service. So the API service will not issue a REST call here, but send a command. So you're sending command through what I termed a command bus just now. And the downstream service will have a command handler that will process this command. This is our first possible enforcement point. This is where we need to start checking for access control. As a result of processing commands, say submit order, if you're a retailer, say, you might get an event, orders submitted successfully. So this event is then transported through something you can call an event bus to surprise an event handler. Now the upper part, you're still inside the same service. The flow is inside of this one downstream service. But in this case, the workflow entails invoking yet another downstream service to complete the entire business transaction. So we're also communicating an integration event, if you will, to the second service, and you get sort of the same flow. The integration event gets translated into a command and so forth. So this workflow involves two services and a number of enforcement points in command handlers and event handlers. Not exactly a trivial case to tackle. But be aware that this is what we call operational workloads. You complete some sort of business logic or transaction. But that's distinct from analytical workloads that I'll talk a little bit more at the end. So we have complex workflows that differ in running time, and we have a number of touch points. How do we sort of make sure that we can perform the kind of checks that we need? So I mentioned Open Policy Agent. This is an open source project. It's a policy engine that is not coupled to message-driven systems in itself. It's a general purpose engine for evaluating policies. You write them in a special language, you package them, and deploy them. So you can write them as regular code. Like in your application code, you can write your policy as code as well. So there are three terms that I don't want to pollute the presentation with acronyms, but these three are useful to know of. So you have something called a policy enforcement point. This is something in your code path where you need to check for proper access. So you do not do that in the code path yourself directly. You hand the decision over to a policy decision point where the actual evaluation takes place. This is performed in what's called an OPA server, and it uses a policy bundle that some administrator has created, tested, and deployed. So the code path and the evaluation point are co-located. If you're using Kubernetes, that would be a sidecar. Your container and OPA server as a sidecar to minimize latency, because you're probably going to be doing a lot of these checks. So if you hand it off and the policy decision point says, yes, I will allow this operation, given all of these attributes you provided, the token, the resource itself, and the environment, you can now continue on in the code path with whatever you intended to do with the resource. So in simple terms, this is the OPA layout. And if we take a look at the command case, it's quite simple. You will, in your enforcement point, in your command handler, hand the command JWT, the token, over to the decision point where the evaluation will take place. And if it's successful, you continue on with whatever task you need to perform. So that's the plumbing, that's the infrastructure. How about actually implementing this? So there are a number of requirements that we need to consider when it comes to messages. I'll focus on events specifically here, but the same goes for commands as well. One is that our invocations, if you call them that, are no longer short-lived. So a token's expiry time, which should usually be very short in order to avoid improper usage should they be leaked, must now be longer. They must be valid for an extended period of time due to our async flow. How much longer differs depending on the workflow itself and maybe individual steps inside of it. So it's on a case-by-case basis. Also, this is critical. This token is not reusable beyond a single message. In the synchronous case that I showed you before, when you do a token exchange, you can use that token in any number of calls between services inside of this trust domain. Here, however, to ensure zero trust, we need to generate a token for every message that gets published and ultimately consumed. That is, we cannot change the fact that this message has a specific token and later on sort of circumvent that. Sometimes you can call it non-repudiation, say. But we need to accomplish this binding. But without it, we are not able to enforce zero trust. How do we do this? Quite simply, we hash in this case, event data, the payload. It becomes a claim in the token, much like my identity is a claim, much like whoever issued the token has that as a claim. The data, the payload is a claim as well. We also include a message ID because it becomes useful as well. So given these factors, we can have a stock change event with some payload, some message ID. Message IDs are usually important because we want to make sure that our consuming the message is done in an idempotent way, meaning typically in these types of systems, we can only rely on at least once delivery. A message might get delivered more than once, but you can easily check on the consumer side if you've already seen and processed this message before. But you take the payload, you hash it, you include it as a claim in the token, you sign it, and then you add the token to the event. So that's what's gonna be the final result. So that's how we publish the event. Again, the actual generation of the token occurs in the separate authorization server. But once we have that and we include it in the event gets published, and now we can consume it. You start by simply verifying the token using the standard token practice. Has this been altered in any way? Can we ensure its integrity? Yes, we can. Second, have we seen this event before? So that's just a general check that is good to include. And here is the vital part. Does the payload match the hash that was part of what we signed previously in the token? If this evaluates to true, we are good to go to the final step. If not, we need to reject it. And here, the final part is the actual access control that we perform. So we take the resource and the claims that we got from the token that are relevant, and we hand it off to our decision point. This is our enforcement point. We get a result back, and then we can continue with the resource operation. Again, should someone get a hold of the token, that doesn't matter because it cannot be used with any other events. It's simply this event that it's relevant for, no other type of message. But as application developers, we need to include this check. If we don't, well, then we are not enforcing zero trust as we should. So that seems straightforward, but there are always some devil in the details that you need to be aware of. So one is this problem of generating a new token for every message. And you have one authorization server inside of your trust domain for shipping, say, that generates all of these tokens. For low to mid volume messaging, that's probably okay, but very high volumes of messages for, say, order processing, where I've seen quite a lot of events being generated and published, this might become a bottleneck. So you have basically two options. One is for each service to generate a self-issued token. That, however, brings another host of plumbing when it coming to certificate management, etc. It's an option, but it's a complex one. A better one might be to simply take an authorization server and make several instances of it and co-locate that, again, as a sidecar, much like the OPA server. So in your pod, for example, in your Kubernetes, you will have three containers: your application container, your OPA server, the decision point, and an authorization server for generating tokens. The previous talk delved into event sourcing. And event sourcing, again, it's a pattern for data storage. So inside of a business domain, in shipping, inventory, etc., you use that to store a sequence of events as your single source of truth that you base all of your subsequent decisions, business decisions on. But these events are stored potentially forever because you need to have them around if you want to replay state. So if you include a token in every event, that means that that token and the user identity will be part of the event, again, potentially forever. Is this a problem? Well, first of all, as we already discussed, the token should be long-lived. So what does that mean? Years or just never expire? That's one option. In reality, it doesn't really pose that much of a problem, again, because the whole problem with short expiry times is you want to prevent access or usage of that token should it leak. But as we already saw, if a token leaks in our case, it doesn't really matter, given that the application developer performs the kind of hash check that we saw. So tokens as part of events, in this case, aren't exactly that troublesome. Someone mentioned GDPR issues previously. How do you deal with that generally in events when you use event sourcing? Events are immutable, so you store them and they're there. Should you go back and alter events? You really shouldn't. What's the option? Well, before you append an event to an event stream, you encrypt certain fields, given some key. And when the user is removed from the system or the account is deleted, you simply throw away the key. That's a simple way to accomplish that. So there is something to consider when you have event sourcing in place. Generally, though, you can tackle it quite easily. Another thing is that events are usually employed for replays. So you want to replay something that happened from a year ago up until now to maybe query certain information. Side effects are not part of replays. So if at one point in time a certain event gave rise to an action, say accessing a document or sending an email notification, that happens once. If you replay events that might result in the same action being applied again, you typically skip that. There's no point in sending an order confirmation email half a year or a year from now if it's already been executed once previously. So replays typically don't include side effects, so we don't have to worry that much about authorizing those actions during the replays. Operational workloads are where access control is particularly important. For analytical workloads, say when you compute a metric or a price if you're using a ride-sharing service, say, does it really matter who I am? That I'm part of this event, that I took a certain ride or used certain rides during a particular month? Probably not. The aim is just to compute, say, a price or the number of orders that have been submitted the past hours or so. So who I am and enforcing some type of access control might not be as immediate as a need as for operational workloads, business transactions. So sometimes it's just to say, we'll skip the token binding, we'll skip this particular zero trust aspect for certain analytical workloads. There is one interesting hiccup when it comes to events. Again, they're immutable and you store them long term, possibly. What if I, as a user, that is part of the token, that is part of the event, if I'm removed, if my account is deleted, I leave a particular service. Well, I'll still be there. We just saw that it's not that big of a problem, but sometimes background processing can be quite long. And if I do happen to be removed from the system, what should happen then? Well, when you create your policy using OPA, and they have a special language for it called Rego, we can check in that policy whether I, for example, my email address that I've used when I signed up for the service, if I'm now part of a set of users that have been removed, and this set will be dynamically updated the moment I'm deleted from the system. So there's a way to enforce it also as part of the policy decision. So we can handle that as well. So in summary, when you implement zero trust, should you implement zero trust? Often it comes down to cost versus benefit calculation. If you operate in a network environment that is insecure in a way, not maybe how it's configured, but you don't really want to trust by default entities that operate inside of that network environment, as an application developer, you go about implementing it. You might not have to do it fully if you have certain negotiations with the network layer and the representatives from those who enforce those settings like firewalls and security codes, etc. So you can implement zero trust not on either end of the extreme, but a compromise that works for you, of course. What I like about it is that access control becomes a strategic concern. It's not something you tack on at the very end of your development. You put it in the forefront directly from the outset. So you need to keep this in mind, and the infrastructure goes along with it, and what you need to do in your code. How do you start? Do you start with every type of async flow that you have? Most likely not. You focus on what you can deem be critical flows. Usually they only involve events. And if you have maybe something that deals with money, that's typically a good candidate. You don't want to be too loose when it comes to kroners and amounts. We spoke about trust domains. You have logical groupings of services that communicate with each other within a certain subdomain, like shipping or inventory or order processing. You can limit enforcement points by simply focusing on communication between trust domains and leave maybe the enforcement inside of the subdomains for later, because you have maybe some sort of implicit trust inside of those trust domains that you can rely on at first, at least. So focus on communication between trust domains, between shipping, inventory, and order processing, get that right, and then focus on what goes inside those trust domains as well. Ultimately, this is a talk for application developers. We want to be able to innovate quickly, produce more features, as long as we have a red line throughout our development that ensures not only secure design by and large, but specifically our communication paths and the async communication style that we've seen. So that was my talk. I do have a thing to plug. So if you're interested in designing and building event-driven systems, I should probably title it message-driven systems, of course. If you want to learn the theory, how you model using events and messages, how you derive a system architecture from it, and ultimately implement a real-world application, then this is a full-packed day on that theme. So check it out using this code or the JFocus booth, or just come up and have a chat, and I'll be happy to elaborate more. But it's a very nice workshop that gives you sort of the totality of what it means to design and build message-driven systems. So that's it. Thank you very much for attending. We do have times for questions, I think. Yeah?
Can you back to the slides where the access token was created, or where you encode it?
Here?
Yeah, exactly. This is done by the authorization server, but so this is done by authorization server. So he's creating this access token,
Yeah.
but well, how do you authenticate against this authorization server? Is that the user JOT, the GVT? Or
So inside of the network binder, so to say, inside of the API gateway, you have sort of implicit trust. So a microservice or a service will simply invoke the authorization server directly. And if you require some specific token, that's a separate one just for calling the authorization server. But it's distinct from this token.
yeah, exactly.
Yeah.
But it's user initiated, right? Or
No, this token will be probably just a setting in the service itself, configured in the Spring Properties file, say.
okay. So you have a special service token that is authenticating the gateway to.
Yeah, so the gateway and the authorization server have their own authentication, so to
Yeah,
speak,
okay.
and each component or service inside of this trust domain or inside of the API gateway also needs to authenticate to the authorization server for generating this token.
Okay.
Yeah.
But can you track back to the actual user that started this? Or is
I mean,
that,
it's included in
pointless,
the access token
Yeah.
and in the JWT. So, yeah, I mean, if you get the token and the user identity and you implicitly need to connect to the authorization server, you see which user identity this was coupled to, if you want to. But it's usually not done. You just trust that one service inside of this trust domain can call the authorization server to get the generated token. That's just a standard setup.
Okay. No, I was thinking about audit trails, and if you're compromised in any way, and if you wanted to track back. So that's
Yeah, I think
what
that's sometimes also vital when you have like supply chain attacks. You have malicious packages that intercept a token or the credentials for the authorization server. Or specifically left this out, but that's just general practice that you need to secure that as well. Yeah.
Okay. Thank you.
Thank you. Any other question? Yep.
Yes, do you need to send this token in the message, or could you send it like in a header, or do they need to be coupled, or is it a benefit?
Usually it's part of the payload this way. So it's Do you put it in a header perhaps? Yeah, but it's not usually because it's sort of a claim almost in itself, so it maybe doesn't really belong in the header as such. I typically just structure it this way, or have structured it this way.
You really need to do that if the original message is hashed in the token.
No, so the hashed payload is the claim, but you need the token to get those claims later on.
Okay.
Yeah.
Thank you. One pitfall that we actually experienced when we were trying to send JWT in the headers together with all the messages, we had pretty similar approach, kinda, but we were sending these JWTs encrypted, and then we decided to rotate the encryption key.
I typically, encryption for tokens is not something I've implemented or come across. I usually just rely on the network layer to handle that aspect, confidentiality for me. The signature for the token carries integrity, verifying that, and finally, non-repudiation, meaning that this token is specifically bound to this event, handles that. That's been my approach.
But same then can happen if you just have signed tokens, because if you then rotate the key, you can no longer verify that actually this JWT token is itself valid, so it basically was the same.
Yeah. I think it's quite analogous to the how long should a token be valid for.
Oh yeah, that's true.
Yeah, so it's sort of the same concern, but yeah, you can extend that or not rotate as often, but you have to negotiate with yourself what is a reasonable compromise there.
But you have the key ID.
That's a long discussion.
Yeah, we can take it after.
Yeah.
Usually you have your key ID in the header. So if you have multiple signing keys, even for encryption or signing, the client should be able to get the public key from the server. So you need to take measure to handle double keys.
This is tricky. This is why we have in general, two levels of defense. So we have encryption on the network layer. That's, for me, just easier to reason about. And then the token for user identity. They're usually you have both, just as for general good practice. But you sort of avoid some of these. You can use tokens for authenticating service communication itself, as well as user identity, but it's kind of tricky sometimes. I don't want to keep you too long because I know there's lunch waiting. So again, just shut up later on during lunch or in the booth. I will be there 12:30. So again, thank you very much.